Nice.
But like now it's kind of just stuck, and people just say it random
That's
time.
fantastic. Well, you literally do leak code tutoring? I think it counts. I think you're good.
Yeah, I had to wear the shirt for the flex.
Oh, you have this shirt? God, giving them free advertising. Imagine.
I mean, it was free for me too. You know,
Fair. Okay, I see it up on YouTube now. Although it does the thing where Google Meet pisses me off, where like whoever's talking it shows us, and then whoever's not talking it disappears. But we can just once it shows like sharing screen or whatever. Brandamir says go 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 go. I don't know if it's a way for us to actually see chat easily or anything.
That was the thing too. That was why I was thinking about the OBS thing, was because I feel like if I pull up the live stream, it's gonna cause weird like double speak feedback stuff. Like,
yeah, that can be annoying to mess with. So I've got the live stream like viewing on my iPad just with like my volume turned down so I can see chat in case there's any questions.
I should try to just view it muted or something, see if that works.
Yeah. So when you do, the OBS has the audio pieces, you can turn some things up and down. So I always have to turn like my actual machine's volume, like my max volume down, and the microphone volume up, that kind of thing. Like you have to mess with that stuff. And like the levels are different. Whereas like Google Meet's nice because it just automatically knows to make the audio levels the same roughly, which is super nice.
Maybe I could in its own dedicated window, and then I could just snap over to that when I look at the stream. Yeah,
potentially.
Okay. Yeah. I can see you. It's delayed by quite a bit, but yeah.
Yeah, it's a big delay. Always is. So I have like Figma installed on my Google Meet or something, so we can draw if we want to. We can also just share screen, I suppose, either way. But the drawing's nice because it lets you both draw on the same thing.
Let's try it out. It's time to experiment.
File.
Install.
Yeah. Can you see that?
Yes. Well, I have to install it, but I got a prompt to install.
Nice. Sound is top in OBS, computer audio down. Branimir is providing commentary. Okay. I think I'm set up then once you get this drawing up and you can start educating us on how SAEs even work, since I only know the high level from papers and never actually made one before.
I was going to ask about that. I was like, do we need some exposition on SAEs?
Yeah, I'd like an explanation of the baseline that you're comparing against, that kind of thing, because it's easy to just get past that stuff and leave everyone confused and want to believe, but whatever. And plus, I might not be fully clear on it, honestly, like TBH, but.
Sure. And by the way, if I share my screen, what does that look like? Does that show up properly? Like,
I would imagine it just removes the Figma thing, right? And puts your screen up, I would guess. I would hope.
Does it? That's annoying if it does. I'd like to be able to just draw.
Oh, it's both.
Or either. Yeah, both is preferable.
Dope. Okay. I like both.
How's it look on stream though?
On stream? Well, my stream's delayed, I guess. I want to see if this pulls up. I think the stream might not be seeing either. I can't quite tell because it's like it's insisting on being delayed. Oh wait, no, it shows.
It does.
So it shows your screen, not both, when your screen is pulled up. Try taking your screen down. We can see if it shows the Figma.
Figma, yeah.
We have to wait for the delay, I guess.
How do you draw on the Figma though, too? I
don't. If you hit the little pencil icon at the bottom,
there's
then it's just with a mouse. I don't know what you're seeing of Figma. I have like a whole coloring palette and highlighter button and everything.
It's like super empty. It just looks like a rectangle with a plus and a minus.
Huh. And the live stream also doesn't seem to want to show Figma. Like it only shows your screen when you share it. So I guess you're the only one who can draw and do anything in this call is what it sounds like. I guess we can one or the other do it, but
let's just use an online whiteboard, right?
Yeah, let's do online whiteboard and screen share instead of Figma. Figma apparently sucks. End activity.
Let me see if I could like send you
a
link or something. Share board, copy link.
It's kind of weird that Figma wouldn't show, but whatever. and then we can both draw on the whiteboard. And if you just share screen, it'll always be visible, I guess. And you can also like share code or whatever you want to at some point if necessary, kind of thing. That should work, I would guess, if we just wait for the delay. You share your screen again, and then we can all see, we should be able to see it then if you share your screen. Or I guess I could do mine too, but either way.
This is what I was saying. Might make more sense to just do the OBS thing, but
well, I think it's all working now, right?
Well, unless, I don't know what the stream looks like, right? Like when I'm drawing, is it showing us on the side? Oh yes, okay, we're on the side. Yeah.
Yeah, it just shows one of us at a time on the side, but like good enough, I think.
So you can see the board, right?
Yeah.
Okay. So what is SAE? SAE is for Sparse Auto Encoder. Auto encoder is going to take some input, put it through our little neural net.
Input embedding vector type thing, like any random vector in a model, basically.
Yeah. And then it's going to try and reconstruct what we put in. So that's the auto for auto encoder. And so typically for auto encoder, we would actually have this middle section be smaller, right?
So wait, the horizontal lines are just matmos. The middle rectangle is a much
neural nets. Yeah.
Yeah.
Maybe I could draw this a little better.
The middle bar was a much larger hidden dimension, obviously, and then we're going to, on that middle section, some kind of sparsity constraint, basically.
Yes.
Oh, so, rectangles, pretty.
Rectangles, yeah. Can I like copy and paste these? That'd be nice. Can I do that?
Yeah. Wait. Maybe not. I can select it.
Yeah, hold up. I'm gonna figure this out because it'll be faster if we could do this.
It literally lets me hit copy and paste, but it doesn't let me actually, like, there's copy and paste buttons.
Whatever, I'm ignoring it. And then one more. So really, in general, these autoencoders could be anything, right? It doesn't necessarily have to be a matmul. This could just be some neural net, right? Yeah. And you could imagine this is your embedding vector or whatever, or maybe it's a vector of activations. That's typically what we're looking at with sparse autoencoders, right? You might look at a layer, like I think layer 8 in one of the GPT architectures, and look at what the activations look like for different input tokens, right? And so you just have this series of activations here. I'm gonna call it, I don't know, X, right? And so the job of this neural net would be to take in X and then reconstruct X. And typically, you would have it so that it gets compressed to a dimension that's much smaller than that of X, because otherwise it's kind of trivial. You could just pass it through, right? Mm-hmm. But in the case of the sparse autoencoders, we actually give it a lot more dimensions. So instead of it being a neural network that sort of compresses this initial embedding, we just have, like you said, in the most basic one, it looks like a matmul, and it has a dimension that's way bigger, right? So we have this like big linear layer that it learns to map this X to and then reconstruct the X from. And to make it so that it doesn't just pass it through, we do what you said. We put a sparsity constraint on it.
On the hidden dimension, the centerpiece.
On the hidden dimension. Yeah.
Yeah.
And so I actually didn't look at the initial paper too much because I was looking at the gated ones this weekend. But my understanding is that you have a loss term that is just looking at like the MSE loss for reconstructing this X. They usually call this like X tilde. I don't really know how you type that, but whatever, right? And then really what we would want is for the L0 norm to be small for this. right? So when I say L0, I just mean like if we were to map every entry to a 0 or 1, we'd want that sum to be minimized.
So
Versus L,
we want a lot of zeros in that hidden dimension and only a
yes.
couple actual activations.
And the motivation for this is that we think these models might store features linearly, right? So a feature might be encoded as a direction in the dimension, that in the activation dimension, and then it might compose them. So that's so there's two hypotheses. They're called the linear representation hypotheses and the superposition hypothesis, which is basically that we represent features as directions in this activation space, and then also that we add them together as vectors. And so there might be several features contributing at any one time. Does that make sense, right? So then the motivation for this big sparse layer is to essentially learn a dictionary of directions. It's to disentangle that representation, right? So it might say instead of having this big dense addition of several directions, let's see if we can decompose it into its principal directions, and we call those features. And then we learn a linear combination of those features to reconstruct X.
So we're assuming that these models have just like directions in the actual full vector, directions in the space that correspond to something, a cat direction or whatever it is, right?
Yes.
And they have a lot more actual things to represent than they have dimensions. So therefore the superposition stuff, they can't give every single direction its own actual perfect basis vector or anything. They have to actually combine and kind of squeeze stuff in, and you end up with the actual, that X, that first little input, has just tons of stuff all thrown in there that's hard to disentangle. And we are doing, in this case, just a simple matmul on it to get to a bigger dimension. And that now that is a larger space, like a larger number of dimensions. And then we want a sparsity constraint and say, okay, let's get only a couple of these to actually activate. We want the minimum number of them, like the middle, the big end, and the circles right there, with the minimum number of those actual entries to activate that the model would need to go reconstruct in the ends. It wants to reconstruct the initial X, right? So it's trying to tease out, okay, of all of the things inside the initial X vector, can we just grab a couple of them and can we see, like, separate them out and actually get just a single number for how much this is activated right now? And we should hopefully find that that activation is correlated with something in the data. We should hopefully see that whenever the activation pops up, whenever that one entry in the vector in that middle long hidden dimension pops up, that like it's always showing up during like code errors or during the color red or something. It should be very clear is the goal, right?
Yeah. And so I'm drawing these circles here. These are supposed to represent the directions that this might learn, right? So each of the rows in our matrix will represent direction that the model learns is useful when it's trying to reconstruct X, and we call these directions features, right? And so the goal would be that for any X we put in, that the model will be able to select only a few of these and find that it can add them up in different proportions to reconstruct X, right? So if I have, I don't know, it might be like cat plus house, or like dog plus house is dog house or something. It's able to only select a couple of these. And the way that we would encourage that is by putting a term in the loss, which gives a penalty for how many of these get activated, right? So besides having it say, besides having it just reconstruct the initial X, this whiteboard is I don't like this whiteboard, but whatever. Besides having it just reconstruct this X, we also have it try to minimize the sum of these activations, because then it has to learn to be judicious with which activations it actually has contribute to the sum.
You said minimize sum. Are we literally doing like sum and then minimize that is like minimize your loss. Is that the actual loss
Yeah.
piece right there? That's
So the
literally it.
actual penalty is L1 loss, right?
Okay, cool.
So L2 we have L2 norm would be the normal norm that you think of like in Euclidean space.
Mm-hmm.
L1 norm is going to be the sum of every entry in our activation. And then L0 would be if we were to think of this this activation vector as like a binary
Zeros
vector.
and ones. And we can't use L0 because it's not a smooth gradient, obviously. It's just the zeros
Exactly.
and ones. So we
Yeah.
have to use L1 norm, which is literally just sum and then minimize that sum as its own loss term.
Yes. And it minimizing the L1 sort of by proxy minimizes the L0, which is what we actually want.
Nice.
Okay. So this is a little oversimplified because so I'm not going to talk about training stuff too much. Like for example, usually you would like do a warm up for this L1 penalty so that I can sort of learn more meaningful representations first before like kicking them out, stuff like that.
Yeah, that makes sense.
But the other thing is that if we have the architecture be just like this is sort of the naive SAE architecture, because this L1 penalty introduces a bias, right? There's no incentive for the model to actually perfectly reconstruct X, right? If we want to minimize that loss of the reconstruction loss plus the L1 penalty, then the model is incentivized to actually just shrink the representations a little bit. There's a bias trade-off.
It's not actually doing anything useful. It's just making every single number a bit smaller, but still not zero, and trying to like reconstruct. Yeah, which is dumb. Yeah.
I mean, you'll still get features out of it. It'll still be useful, right? But the point is that from that paper, there's this paper right here. Let's look at the gated sparse auto encoders. They find that it's like a Pareto improvement. Basically, it's better in every way to separate out how do I name these? Maybe I should just see what they name it in the paper. They separate out the magnitude of each contribution and then whether it actually should contribute to the sum. So they put a gate, right? So basically, instead of having just this, right, we train it to say, this is, if we were to use this direction, this is how much it should contribute here. Maybe it would do 0.1, right? And then if we were to use this direction, it should contribute 0.5. If we were to contribute this direction, it should only do this much, right? And then we pass all of these contributions that it learns through a gate, which essentially says that decides whether the contribution is big enough to actually include it.
So a ReLU with a bias is the oldest version of that gate, right?
Yes. So we pass it through this gate. It's essentially a heavy side. It's a step function, and it says if this is bigger than 0.05, then include it. If this is bigger than 0.4, then include it. This is bigger than 0.2, then include it. So this one wouldn't get included. So it learns separately how much each direction should contribute, and then how much each whether each term should be included. And doing this separation makes it so that that shrinkage gets nullified essentially, because the parameters that are responsible for doing the learning the contributions aren't sort of biased by that L1. The L1 comes in from the gate parameters. Does that make sense?
Wait, I half zoned out. The L1 is not applied on the original activations. It's applied after the gates.
Yes.
Okay, cool.
So we actually introduce a third term here, which is that we have a reconstruction loss, which we have from this layer, which is our activations. And we see how well that one reconstructs X, right? And then we do the L1 penalty on this gate.
So
instead.
there's a parallel path here, one that's just pure easy reconstruction and one that is the actual gated and L1 loss reconstruction.
Yes. So there's actually
Nice.
3 loss terms that we consider. And so you might have seen that in the graphs like I shared over the weekend or whatever, right? I don't know. Can you see my screen?
Yeah.
There's a graph somewhere here that I have 3 losses I might be looking at while I'm training, right? I have my MSC loss in blue, which is just looking at input and output. How well was the embedding recreated?
Yeah.
Right. I have my sparsity loss, which is saying how good of a job is the model doing at reconstructing it with only a few terms, right? Versus using every entry in that middle vector. And then I have my auxiliary loss, which is basically saying, so I should say the sparsity loss a bit differently. I should say how good is the gate doing at only selecting the directions it really needs. It's probably a good way to say it.
So
right?
it's still a reconstruction loss, but it's reconstruction from the gated part.
No, the sparsity loss is just how many entries are actually getting through.
That's the actual just direct L1 loss. That's all that is.
Yep, this is just L1. And then the auxiliary loss is if I were to look at the activations before I gate them, how well are those reconstructing my input embedding?
Oh, so the MSE loss is with gated, like from the gated sparsity parallel path, and then the auxiliary loss is the just no gating, no sparsity from the original full vector reconstruction loss.
Exactly.
Okay, cool.
And doing that allows the gradients to go through better, right? Because the gate is going to introduce like a non-differentiable. There's going to be like there's going to be a point there where it just sort of skips.
You'd have a lot of dead neurons if you didn't do this, basically.
Yes. Yeah.
Okay.
And so that's sort of the overview of like what we have. One more thing is that it's not clear when people present this. I don't think like I've learned this weekend is that the encoder and decoder weights, they can't be allowed to just have whatever value, because if you let the encoder and decoder weights sort of just have whatever value, you'll get like degenerate behavior. Basically, you need to constrain one of them, typically the decoder, to have a fixed norm so that it doesn't do a naive optimization. I feel like they say this better in the paper than I would, but the point I'm making is essentially that you could, if you allow the encoder weights and the decoder weights to sort of just have whatever value, then the optimizer will sort of just push them in a naive direction that isn't actually meaningful, that helps game the loss a bit.
So I'm not clear though, like in what way is it gaming? What is the norm fixed to, and how does that help? I'm not clear on that. Like, because we were clear on the whole gaming loss earlier with the L1 sparsity and everything, but how is it gaming encoder and decoder? So it's the same encoder. This is a good question actually. It's this for both parallel paths. We're using the same encoder and decoder, like the same matrix, correct? Like it's just one MLP effectively, but just calculated twice. Like
no, you do allow them to be separate. So I should say this. Yeah, the encoder and the decoder weights are different, right? We have a matmul that brings us from X, the activation dimension, to the dictionary or hidden dimension. And we have a matmul that brings us from the hidden dictionary dimension to the original activation dimension.
Yeah.
Right? Those are two separate linears.
My question was, do we have two separate decoders? Like, is there one decoder for the full hidden and one decoder for the sparse hidden? Or is it just one decoder being shared for both of those?
It's just one.
Cool.
But okay. I should say so this takes two separate paths and then it gets added in, right? So you could sort of imagine, right? Remember the initial architecture we talked about where this was just one layer? This new architecture looks like it doubles the parameters, right? Because I essentially have a matmul that goes from X to the activations, and I have a map model that goes from X to the gate, and then I multiply the gate and the activations together, and then I decode, then I decode that.
Wait, so there are two separate encoders then? Two separate encoder map moles? I thought it was.
Yeah,
I thought it was.
there's a picture in here that might be more clear.
I thought it was input single weight matrix for the encoder, and then just we take the full inputs, we gate it, and now we have both the full inputs and the sparse inputs, and those use the same decoder map mole is what I thought.
Can you see this picture right here?
So encoder, presumably a map mole.
Yep.
One of them gets gated, the other gets scaled and shifted. Okay, which that wasn't mentioned earlier, but that's fine.
So this part right here, right? This is our contributions of each direction to reconstruct our X. This is the vector that we would use for that auxiliary loss right here. And this right here is just our binary vector telling us whether we should keep the contribution or not. And then here we just multiply them element wise, right? And then this is our gated output. It's this, but with some of them zeroed out.
Oh, okay. So this is a glue. This is a gated linear unit, not an actual MLP, like not a traditional MLP. Okay. And
yes.
the gated linear units is so encoder WN is just a single map mole to a higher dimension, obviously, like an up projection. And then the gating one, whereas usually in a gated linear unit, you'd have actual two separate up projections, one for your up and one for your gate, right? Here it is one single map mole, and then the gating gets just a bias term, just a biases, and that turns into a gate, right? And this is
that's what I was going to mention, was that the way that they prevented it from doubling the parameters was by sharing this initial weight matrix and then only having it learn biases for each and
That's
like
smart.
a scaling for each, right? So instead of having a whole separate encoder matrix, they basically said we're gonna assume that the magnitude and whether it should be included in the sum are correlated, and we're just going to learn a scaling factor and a bias. And so the other way you could think about it is that for each of these rows, it learns this sort of jump ReLU function, where it essentially learns for this row or this direction, right? This is how big the activation needs to be for it to be included in the sum. And so you can sort of see this jump ReLU graph here, right? So for maybe for row 1, if it's above 0.1, it'll be included in the final vector. And maybe for row 3, if it's above 0.5, then it'll be included in the final vector. And otherwise, it's all zeroed out.
Okay,
So
and then
think about it. That's why I drew it as a like an MLP.
Cool. And then the gating path, is that actually zeros and ones? How does the gradient work there? Like, how does that path receive a
So this is what I was
thing?
talking about here. This is where we introduce that discontinuity, and so the gradients wouldn't go over very well. And this is why we have the auxiliary loss, where we look at this vector and how well it reconstructs instead of just this one, because it does introduce a discontinuity here.
Okay, interesting. So the gating one is fully broken gradient, the gating path, and then our two parallel paths for our two parallel things are actually both part of the upper, not the gating one, the blue one. Okay.
And so looking at this loss function might help a bit, right? X is our input. Essentially, we learn a gate threshold. We learn a threshold, and we also learn a contribution. And we introduce, so this sort of 1 greater than 0 thing is supposed to represent the Heaviside step function. You know what that looks like? It's this sort of like jump from 0 to 1, right? It's just a gate.
Yeah.
And then we would multiply this entry-wise by each activation. So this activation is probably what you're intuitively thinking about the SAE learning. And this gate is maybe the less continuous sort of strange artifact or whatever, right?
Okay. And then am I correct in thinking that a lot of what you see in terms of different SAE proposals has to do with the gating path. Like I saw OpenAI propose instead of using ReLU or something or whatever gate, instead they use top K or something. Is that the case? Because I see there's a gating path. There's also a ReLU. I'm just curious
Yes.
if you're aware of the other methods of like the dozens of different SAE alternatives proposed. Like my impression is, wait, interesting. I don't know what my question is exactly. I'm not quite sure, but
The issue with L0 is the differentiability. What's wrong with L to 0.5? Too much more expensive to calculate? Interesting. What would L 0.5 be? Would that be like a square root norm?
I have no idea. Square root norm?
Well, part of it, right, is like when we look at these norms, there's a certain shape that they take. I don't want to get too far off track, right? But so like if you were to look at like let's go to Desmos real quick. These norms correspond to different like circles, right? Like in 2D space, we have x squared plus y squared equals 1. This is like what the L2 norm looks like for unit norm, versus this is what the L1 norm looks like, except we would have 4 of these. Maybe I should be using absolute values here. Would that fix it? Yeah, right?
Yeah.
So you could sort of imagine if you have your loss function that's sort of like coming in and out of the screen, that this norm is going to intersect with it, right? And what we should expect from the L1 norm is that it sort of hits it at a corner first. Like if you ever took a linear programming class, you would know that like for convex functions, it's typical for them to have minima or maxima that are at like corners, right? And so part of it is the other thing I didn't mention, right, which I was going to bring up, but we sort of got sidetracked a bit, which was that I was talking about how the decoder needs to be constrained. Typically the way we constrain it, but by the way, let me see if I can find why it give me like 30 seconds and let me see if I can find a better
No rush.
explanation of why it needs to be constrained, because they word it better than I'm wording it. But essentially my understanding of why it needs to be constrained is that if you don't constrain one of the encoder or the decoder weights, then it can game the penalty by just allowing them to be smaller, like when you add it up, but then like scaling it back up.
Yeah. We discussed that earlier, I think. Yes, that makes sense.
But so the way that we mitigate that is by saying, all right, this is why I keep referring to it as directions, right? Let's go back to this right here.
Wait, I think I got it. Sorry. Let me correct me if I'm wrong. You have to force the weight matrices norms to be a certain level, because the whole gaming thing with the hidden layer with the middle part.
Yes.
When you force the weight matrices norms to a certain level, they cannot then become big. They can't become big to compensate for the small
exactly
hidden layer. Yeah, I got you. That was the same thing as earlier. Then that makes sense. Okay.
Yeah, but so then what that implies is that each of these directions that the decoder is learning, right? So the decoder is going to take each of these contributions and add them up.
Mm-hmm.
Each of these directions that it learns, since we need to constrain it, we constrain it to a unit norm. So basically, we allow the encoder to vary however it needs to reconstruct things properly, right, with a minimal loss. But the decoder, we say, hey, you're gonna keep a fixed size so that you can't sort of game the L1 penalty.
And if
right?
the size is unit norm, does that mean it's cosine similarity in the middle?
What do you mean?
Like
I understand that.
If you have two, I guess this isn't quite the case. I just jumped to the fact that if you do have unit norm going on for everything, I don't know about everything, I think you just said decoder maybe, then whenever you have two vectors that are both unit norm dot product each other, then what they actually have is a cosine similarity. So if everything in here were unit norm, then you could interpret the middle activations as cosine similarity. That's not like, but I don't think that's the case because
Well,
the input is not unit norm.
so maybe the picture that would be better, right, is that for each of these rows, we're going to have a vector that corresponds to it. So maybe for this first row, we have this vector right here. And maybe for the second row, we have this vector right here, and so on, right? This is why they call it the dictionary, by the way. Each of these vectors represents a feature under the linear representation hypothesis, right? So like this might be this one. And this, so what the model is learning is to say, hey, take this feature, scale it by 0.1. It's like what you learn in linear algebra, right? You're supposed to be thinking of these as near-orthogonal. They're basically your basis. It's learning a basis, and the bases are features, and this is each of their contributions, right? And so then if I were to follow what I drew here, maybe I'd scale this down to like here, and I'd scale this to here, and I'd scale this to like some super tiny thing, and I'd add them all up tip to tail, and that would hopefully reconstruct my original X, right? We constrain each of these to be have a L2 norm of 1, so that they essentially act like how we normally think of basis vectors, like the principal basis vectors in linear algebra. We're essentially learning a basis for our feature space.
Okay. Yep, that makes sense.
And that's what our dictionary is, right? And so, but by the way, do we feel like we got a good overview of what?
Yeah. I was about to say, I think I'm happy to move on to the tree idea and everything at this point. Yeah.
Okay. So you went over this paper a while ago. This one, Towards Model Semanticity, very popular paper.
Yeah.
And what some of their findings got me thinking quite a bit, right? Because one of the takeaways was like, hey, if we ever actually wanted to look at all the features, the amount of training it would take would be insane. And that made me sad, right? But there was a picture in here somewhere. Maybe I'm looking at the wrong one, but basically they found that these features come in clusters, right? And they even observed feature splitting, right? Where it's like, hey, look, we have this feature that right here. So we have these clusters of feature directions, and we found that when we upped the dictionary dimension, it was able to learn what previously corresponded to a single base 64 feature to split into 3 separate ones or something like that, right? And so that got me thinking, like, there's an implicit structure here that we might be able to take advantage of. There's a hierarchy, right? Like the other way to say it is, let's think about how do I say this better?
Let me try and clarify what was happening. So like, let's say your hidden dimension, the center of the model, originally had, I don't know, 100 actual activations features, right? And one of them was San Francisco. When you then trained a bigger model that instead had 300 hidden dimension, whatever features, they found that whereas the small 100 length model had 1 neuron for San Francisco, the 300 length one, that San Francisco neuron was no longer there, but there now was a Golden Gate Bridge neuron, an Alcatraz neuron, and a homeless people neuron in the streets or something like that. Like whatever, like 3 traits of San Francisco, right? It found that there were now 3 features that highly correlated, like we're all subcomponents of the original feature in the smaller model. And so it's like, oh, this just seems to go forever. Like we can make bigger models, bigger SAEs, and like this just keeps getting, like it's just gets out of hand kind of thing. And these things are very expensive to train because you have to actually run your entire large language model, your Claude, Opus, whatever the heck it is, just to even make the training data for this thing, right? Every single individual vector. And they were like, well, do we really need billions of tiny little features like that. How do we use it? What's happening here? And your idea was, can we find a way to, instead of training a new model from scratch that's a much larger dimension and much more granular features, can we find a way to train that small model with just San Fran and then split that San Fran neuron into the three subcomponents and like do that hierarchically and continuously, and we just like we get more and more splits onto features that we actually care about, as opposed to every single new big model run getting a random cluster of very, very tiny features type thing.
Exactly. And you know, that strategy wouldn't be that bad if we couldn't make assumptions like this in the data, right? Like if we found that the features were like very randomly and like had a high entropy, just sort of like very like a diffuse clustering, then maybe it would only be possible like that, right? But because of this observed clustering, I would expect that you could do what you were just describing, right? Which is sort of train it hierarchically.
Mm-hmm.
I don't know how to say that properly. The other way to say what I was thinking about, right, was like we're calling this dictionary learning, and it makes sense because it's like we're essentially learning a bunch of entries which correspond to some meaningful direction, right? But it wasn't clear to me in this paper. Maybe I need to read it a little bit more thoroughly. How they're actually navigating some of this, right? Because some of the other difficulty besides the training costs is just like it's also really big. How are they actually verifying this stuff, right? I mean, there was some automated like interpretability scoring, but in terms of like identifying the split, right? How do they know that it was the split from the initial direction? It looks like it's manual inspection. You're sort of cross-referencing token activations and
I would
stuff.
assume it's correlation, right? So like if you have two SAEs, one small, one big, on the same like LLM underneath, whatever it is, right? If you run both SAEs on the same input data to your LLM, and then you just do that a lot, and then you try to correlate between your small and your big SAE, I imagine you could get out, oh, these three of the big SAE correspond to this one neuron, like high, like 0.8 correlation or something of this one neuron in the small SAE, right? Am I wrong there?
I believe so. This is the picture I was looking for where they have that base64 feature, and then you can see that the same tokens were sort of having high activations, but split into three different categories right here. And this is what they were referring to as feature splitting.
Mm-hmm.
But what this got me thinking about was like one of my professors showed me something a long time ago, which was like he was talking to me about memory addresses, and he was saying, hey, you know, a memory address is more than just a label in a big space you have. Like, you know, if I have my big, this is my memory space, and I have a bunch of addresses, like maybe this is 0x00001, and this is, what the hell is that? Hey, the copy paste finally worked.
Nice.
So that's really small. Can I make that bigger? Maybe. Yeah, there we go. So maybe this is address 1, and this is a. Hey, there we go. Faster. This is better, much better. You know, maybe this is address 1001, and this is address 11111 or whatever, right? What he was telling me about was like the number isn't. It helps indicate to you like what partition of the memory it's in, right? Like if this first bit is 1, then we know it's in the larger half, like the second half of the memory space. And you know, if this bit is 1, then we know it's in this half or whatever, and it essentially refines us down to one specific entry.
Mm-hmm.
And so the point there is that this architecture is useful. It gives us a list of a bunch of useful values, but it's like unordered, right? And so we can't sort of do this like a log finding something we want, because you could normally do that with a dictionary or a phone book too, right? like you don't just like look through the dictionary or the phone book word by word to find whatever feature you're looking for. It's like I'm looking for cat. I flip open to the middle of the book, and if the words start with a D, then I can omit the second half of my book, and I do that until
your binary search.
Yeah, and I get to see. And so I was thinking about for here was like, well, maybe we could train that smaller model, like you said, and then use one of the other papers you looked at to sort of like learn from there. And then we could use the fact that the second model was derived from the first to impose this hierarchy on it.
Mm-hmm.
So really simple picture, like over simple, would be like, is this finally gonna work now? I don't. Hey, I'm figuring it out. Nice. We're making stuff faster. All right. So pretend this is our autoencoder. We have our X, we have our X tilde, and let's pretend we only have 2 useful directions that we've learned. So this is the really bad dictionary, right? We might say for some specific X that it learns to activate like this one at, so let's also do the simplified view where we're not thinking about the gate. Just pretend the gate is there. We're using jump preludes or whatever, right? So maybe this one learns for this specific X, it learns, hey, this should be this is the one that should be activated completely, and this should be just 0, and this is like our best faith reconstruction of X or whatever, right? There's a paper you went over, which was called Scaling Smart, where they found you could like,
oh, this is your connection. Interesting. Keep going. Okay, I'm here.
You could copy the output logics of a matmul by like concatenating the original weights, right? So let's say I had a initial layer that took in an X and outputted a Y, and I wanted to make a new one that took in X and outputted 2 copies of the Y's. Then I could just concatenate these weight matrices together, right? And so what I was thinking about for over here is like, all right, let's do that right here. So the same input, but now we just doubled the dictionary dimension, and we kept the same directions, but we've duplicated some of the directions and overlaid them a little bit.
And then what all you have to do there would be to keep training, because the model would instantly say, hey, we don't need 2 of these one feature for all of these, right? It would start messing with one or the other or both, I guess, or right? Both,
yeah. Or the other way,
you could freeze the first half too, I suppose.
So this is what I was talking about when I was DMing you earlier, when I was saying my mental model of it changed completely. So really my goal here is like, hey, if we could do this, we might be able to observe the feature splitting versus just looking at correlations. We might be able to say, hey, look, this is a useful representation that a sparse autoencoder found. Now I've given it more room to diversify its vocabulary, and I want to watch it split the feature. Or the other way.
Those 1.0s would then probably turn into something else that represent sub features, basically.
Exactly. Yeah.
I'd be so curious to know like what makes sense in terms of splitting. I would want to do almost like, because remember that the whole functional preservation thing of the previous paper just now. Basically, you have to either double or quadruple or power of 2 whenever you're going to functionally preserve anything. What I'd be curious to do is I'd say, okay, let's take our initial set of features, our initial 2, let's do a ×4 size increase, and then the first one freeze all of the weights that have to do with that, those original ones, basically the first of the 4 groups. Let's freeze those first ones to keep that still in place. Like that's still a held in place feature. And then the next three, all those three copies, let them do their thing and see how that differs from what you have here, which is just like a naive splitting, in which case I guess both of the 1.0s would become like a 0.4 and a 0.6 or something for two separate concepts.
And well, something too is like we only need to do that doubling if it was case 3, right? But here we actually have a case 1 and a case 2, right? So the encoder is going to be case 1, right? We need to go from the activation to double the hidden. And for the decoder, we have a case 2. Or maybe I swapped, but you get my point. Right?
Yeah.
And so you could
not
do
swapped,
like,
you're correct, yeah. But keep going.
You could multiply by 3 or 5 or 11 or whatever if you wanted to, and it would be fine. I could make the dictionary dimension 11 times larger, right?
Okay, I was thinking powers of 2. You're right, though. That's awesome. Okay, sick.
The other way, and so this is, I gained a new intuition from this sort of, since we know that this decoder rows are unit norm constrained. By the way, what does that look like? That means that when we do our gradient step optimization, we need to project back to the unit sphere, right? So I have a picture of this in Discord. I think it's in here. Right here. We know that our decoder, our directions live on this unit hypersphere. And so when we update it, right, when we get a gradient from Adam, we only take a step that's tangent to the unit hypersphere, and then we make sure that we
pull back down onto it.
Pull back down onto it, right? So if it says, hey, your reconstructions would be better if you move this way a bit, we take a step this way and then get back on the sphere or whatever, right?
In this picture, it's if you're at C and your parameter update from Atom or SGD, whatever, says go to D, then it pulls you back to E.
Exactly.
Right?
Yeah. Yep. And so the intuition I didn't have before this weekend for how you could visualize this is that you think about, like, I have my sphere. I really wish I could make this oval dashed.
I get what you mean, though. It's meant to convey 3D. Yeah.
Yes, is a 3D sphere. You could imagine your dictionary is like a collection of is this going to get in the way? Okay.
You can just do a 2D version of it because it's fine to do 2D, right?
Pretend this is 3D, right? Or 4D, or however big your dictionary size is, right? It's a hypersphere. You could imagine that you have a bunch of arrows coming from the center, essentially. And this is your dictionary of, like, what is going on? This is your dictionary that you've learned of, like, useful feature directions, where it's like, hey, if you're only allowed to have 12 vectors, these are the 12 directions which are the best at being able to be recomposed into activations. Right, so this one might be cat, and this one might be house, and this one might be San Francisco, and you add these up in different amounts to reconstruct your original X, right? So each of these rows would correspond to one of these vectors, and the amplitude would correspond to, like, what you scale it before, and you would add them all up tip to tail to try and get your original X vector. And so these live in the same space as X in terms of what dimension they are. And we also know from the paper that we actually expect these to be pretty clustered. We'd expect there to be, stuff like this or whatever, right? And so, well, we could think of this doubling thing doing, maybe I should indicate that with, like, a square or whatever. This is our doubled. This is our copied one, is that we're essentially introducing another vector in the exact same place for all of these, and then allowing it to readjust.
Nice. Yeah, and so I mean? Yeah, so and then as we continually train, then suddenly those two vectors that are overlapping, because, like, we initialize them with, like, these copies are the same place, they get to now separate from each other type thing. Or you can freeze one, let the other separate type thing, or freeze one and have multiple copies and let all the copies separate out.
And you can imagine for this sphere I drew right here, if I only allowed the model initially to have 5 vectors, it might learn these 4, and it might learn this one, and this one will just end up being a good approximation for these 2.
Yeah.
Versus now I allow it to have 10, and I'd start them all at the same places. This one might learn to sort of diverge into these 3 and have a better reconstruction loss.
So when it comes to like when we're doing this, I guess the question that comes to my head is, these clusters, there are different size clusters. Some are like huge, like some are relatively more sparse, some are relatively more constrained, some have lots of actual features in them, some are like not that many. There's probably a couple just standalone features almost, or like borderline standalone out on their own. We're doubling, when we double like this, we're doubling everything, right? And so then when you start continually training, the question becomes like, okay, what happens to every original direction's new copy neuron? And it's like, my question is, so obviously for the ones that we care about, the splitting, the try, that's what I was gonna say, like the ones that are like in a clear cluster that like have more actual points in that cluster they can represent still, then they do the whole splitting and being nearby thing. But I was curious, like, what's going to happen like to the entries that are somewhat alone, or that are just have like that now have too many vectors for the actual cluster? Are those extra copies, are they going to jump somewhere else on the actual hypersphere and like lose their correlation with the previously related like thing they're copied off of, and they're gonna like or are they going to just like sparseness wise become dead neurons?
And so I actually ran some experiments this weekend. I'm nowhere near done where I want to be, right? But we can actually answer a couple of these questions, right? So one of them is like, here's just some code for is this code visible, or is it like too small? It's like really small.
I can't see the stream yet, but it looks fine from my screen.
Okay. These functions do what you would expect them to do, right?
Yeah,
they
barely readable on the thing, but that works. It's fine, I think. Yeah, that's probably better.
There we go. So we take our weight, for example, and we let's see, is there we concatenate several clones of them, n clones or whatever, right? I detach all these from the gradient graph so we don't have weird side effects from the concatenation and all that, right? But this does what you would expect. It's sort of just like it creates a new version that's either been widened or expanded, however you might expect, right? I have a gated autoencoder class, which has what we described, right? We have our decoder bias and our gate bias. And we also have our encoder and our decoder that take things from the activation dimension to the dictionary dimension and back, right? And I'm not going to go too much into the details of all this. I add this method called expand dict size, and it defaults to 2, and it just widens everything that needs to be widened, right? So the encoder output gets doubled, and all of the biases that need to get updated and such get duplicated as well. So this does that operation right here, where we sort of just like keep everything the same, but duplicate it in the appropriate place, right? And this is our constrained optimizer. It takes the decoder parameters and it makes sure to project them back to the unit hypersphere, right? So that's what this is doing right here. We're taking the norm, we're taking that away from the gradient. This makes it so that the only part of the gradient that we're looking at is on the tangent plane, like in the picture from Discord right here. It's projecting onto this tangent plane, and then once we do our step, we make sure to renormalize it back onto the sphere. So we step along this plane, come back to the sphere. That's what that constrained atom looks like here. But so I just took a data set of a bunch of word-to-vec embeddings because I'm more familiar with them and I know they exhibit this linear representation. And so I wouldn't have to worry about like if
It's a lot
the
cheaper than a full LLM. A lot cheaper.
exactly.
Yeah.
Yeah. Because I was just like, I want to see if any of this actually like even makes sense, right? And in this graph is actually cut off a bit, but so I trained a I think, what is this? I think this is so the Word2Vec embeddings have 300 features, 300 rows, and I started a gated sparse auto encoder with like 8,000 192 rows. It's a power of 2, whatever, right? And I cut it off, but if you were to go back several epochs from here, the reconstruction loss would be way bigger than the sparsity loss, just because there's so many dimensions.
You always
right?
gotta do that. Yeah, that makes sense.
But it's so big that it like swamps the rest of the graph, and it's sort of irrelevant because it's just like a bad initialization. So I cut it off, whatever, right? Here, what I did is I let it get to a place where it's basically converged, right? And then right here, I doubled it, and I let it continue training. And so one thing that's pretty cool here is we could see that the doubling operation had a really minimal effect on the loss. Like it didn't disrupt the loss, right? Like if
because you're still just it is a functional preservation. Like it should be the exact same thing as the output, I imagine. Yeah.
I did some more naive ones over here, and you can see that the loss has these huge spikes, and so it's like hard to tell whether the new state that it converged on is sort of just random because of some annealing process, or if it was actually because it like leveraged the original configuration.
By naive, you mean like you added the new amount, but it was initialized randomly, not with the actual preservation functionally.
So there was another method I tried where I doubled the hidden dimension, but it what happened? But it made it so that the how do I say it? It made it so that this sum doubled. And so obviously the reconstruction loss got really bad because
you forgot to do the divide by like normalization. You missed a little tip in the paper. Yeah, I got you. That makes sense. Yeah.
And so you can see that there is a doubling operation that is like really disruptive to the loss. Versus if you have it tuned right, it really doesn't. Very crazy. But you can see that it did have an effect. The sparsity actually started going up, loss started going up a bit, and the auxiliary and reconstruction loss went from flattening out to slightly going down a bit. And I think this could be a lot more dramatic if you were to do like a warm up on the sparsity, where essentially you say, hey, don't worry about the sparsity too much initially, and just start having better directions first, and then sparse it out.
Because are you worried it might have just been killing neurons out of duplicates kind of thing?
Yes.
Yeah.
Well, not only that, right? But remember the part of the graph that I said I cut off?
Yeah.
Initially, this is way bigger than this, like a lot more than this, like 2 orders of magnitude bigger, right?
Yeah.
And so it dominates the loss versus here, the sparsity is dominating the loss, right? And so if we wanted it to behave more like how it behaves when it starts training, we would probably want to reduce the sparsity penalty just so that it sort of mimics that initial state that it's in the beginning, right?
This is why I'm also curious about like freezing half of it, like when you double size, like freeze one side and like let the other one go or something. Is like there's a lot of things to do here. And question, when you did the whole like in the Apple paper, the doubling, were you doing the one that actually had the noise added?
No, and
you were doing noise.
I'm doing it noiseless. I tried I didn't do this experiment with noise, but I did implement it so you could do it with noise. It's not clear to me that there would be part of the reason I wasn't too concerned about it was because in the paper the one without noise was still like in the top 3 for performance. So I was like, this is probably an irrelevant hyperparameter that's going to increase complexity of my implementation, right? But
I'd still be tempted just because the way you're doing it right now, the vectors are both in the exact same spot, right? Yeah. Which double encourages one to just die. Whereas if they are slightly pushed away, like slightly off from each other when you start, then it's like, oh, maybe they actually can, maybe it's easier to find an actual useful place to gravitate towards if they are from the beginning not given a direct copy, but given a slight offset of each other.
Yes. Well, that was the thing too, is like the noise is like mathematically not like the directions are still maintained. I don't know. It's a strange artifact, and to do it, I would have to keep it in separate linears instead of concatenating it the way I am if I wanted to like freeze one of them like that. Unless I was like going into the optimizer and like zeroing out that part, which would be kind of strange, but I guess it could work. But I wanted to circle back onto on the question you had earlier though, because it ties into what I was talking about on the server, and it lends itself well to this other way of visualizing it that I recently thought of, right? Which was, you were saying, how do we know the difference between ones that are like just isolated versus in these really big monster groups, etc.? Like it's kind of naive to just like give them all like n copies or whatever, right?
Yeah, because they're only chosen based off importance, not based off of density of their own cluster type thing.
Right.
Yeah.
And so there was a couple things I was thinking about. One was that for these clusters, it might not even make sense to learn new directions like this versus what might make more sense is to learn the differences.
Okay.
And what that might look like is I might say,
is this the MOE thing from originally?
Yes.
This is what made me like ask for the calls. When you said an MOE version of like, I would like to, like, that's what I was thinking at first, is using like in this like display we have up here, the 1 and the 0, right? Using that as your actual MOE gate or something, and just doing a new with larger dimensions sparse autoencoder on top using this as an MOE gate or something. That makes so much more sense to me. I like that a lot. Yeah, keep going. I'm explaining very well.
So the thing I was thinking about was like, if we go back to this picture right here, if we want to learn a new cluster like from C, like let's pretend C was a direction that we found useful, and we expect that there's a bunch of features surrounding it. What might make sense is to just initialize like a bunch of new vectors that are pretty small in like a circle on this tangent plane, and let those sort of converge, and add those up with the original one.
Would it even be the tangent plane? I guess it would, because they have to go back to the center thing. Wait. Sorry, keep going. Yeah, I'm just processing.
I haven't thought about too much like, hey, how do we know which ones have a bunch of features around them versus not? It seems learnable. I would expect it to be learnable.
I would imagine, just like, let's say you actually start with a very small number of features, like 16 or something, right? Can you not initialize, like once you have your first setup train with your 16 hidden dimension of your SAE, can you not now initialize 16 new sparse auto encoders, right? Of each, like, I guess each of them also hidden dimension 16 or something. We could do a 2 base or whatever. And then just like use the original SAE as like your MOE setup, like as your router. Yeah. And then whenever you start doing this, you see like, oh, this one actually had a very high like add to the loss, like it actually helped the loss a lot, and like of the 16 that you newly made, oh, this one helped the loss a ton, and it's like using as many neurons as possible, has very few dead neurons, whereas this one like only has 2 useful neurons. There are 14 that are dead. Let's just slice out the 2 useful neurons, concatenate that, right? And like and just like, I imagine like a adding and pruning, trimming, like MOE setup almost as you go kind of thing, if that makes sense.
Yeah. So that was the other thing that was appealing here, right? Was like, so this initial idea, I said the tree here is more of like a theoretical tree. We're not actually reaping any like space benefits. It's more just how we're thinking about organizing the data. It's sort of like when you think about like a heap or something, right? Where it's like this is our left and right child, but we're still just doubling the dimension. It's a lot of space, right? And one of the other things you touched on when you're looking at towards monosemanticity is like, if we want to learn a lot more of these features, not only is it expensive because we're having to train like from scratch, but it's also expensive because we're having to just train a lot of vectors. Like we might need billions or like trillions of rows, and that just requires a lot of compute and a lot of memory.
Whereas under this dynamic, you're only training the final number of rows in that final little epoch or whatever, and most of the actual training time is spent with way fewer actual rows being trained.
Yeah, my thought is that if you were able to sort of treat this initial SAE as a router and then make these sort of children and train it in a mixture of expert style, that you might not need anywhere near as much compute because you could represent a lot more features as compositions of other ones as sort of like a, you basically would only ever have to worry about a path from root to leaf, or a couple of root to leaf paths versus a fully like dense tree, right? Where we have to look at every single leaf. So one thing I was thinking about was like, it seems like it would be true that the directions that correspond to clustered features would have a lower gate bias because they are used more often to reconstruct more activations, right? Rarer ones that only have one, they're isolated, they will be used less than one that has 50 little slightly more useful directions, because that 50 sub feature one that gets approximated when it has to be ends up getting reused a lot more in all of those 50 cases.
So you do think that like the model was trained off importance, not off cluster size, but you do think that cluster size and importance are probably highly related?
Yes.
Okay. Interesting.
That's my hypothesis. I haven't ran an experiment yet, but I got to start somewhere, right? I that makes sense to me as being true. But so then, yeah, that was one thing I guess I wanted to try and work out a bit on this call. It was just like, I'm not sure what the MOE architecture would look like, assuming we have some SAE here that's converged on some useful dictionary. Is there a way that we could think of to use the SAE as a router and initialize some experts such that it would be able to learn from here in a more like compute efficient way and represent. Oh, there was one more thing. So
one more thing before we get to trying out the MOE stuff. Okay, yeah.
So we talked about how there might be benefits here in terms of not having to train from scratch or having to use less parameters. But the other benefit, if this can work, is that it allows us to automate labeling and grouping features, which might make them more interpretable and discoverable as well, right? Like remember you were just talking about how like, oh, San Francisco could split into homelessness,
Alcatraz and Golden Gate Bridge, or
Golden Gate Bridge or whatever, right? In general, it would make sense to sort of start from like big ideas and refine them down to more specific ideas. And this process seems to do that pretty explicitly, right? I would almost imagine that you could like say you could use like ablation to amplify these initial features and get like a LLM to class to like name what these amplify. And then because if you look at this paper, right, these labels are like super sort of
random, and have the LLM decide which ones we should actually do a new one on. Like tell the LLM we're trying to like our purpose is alignment or something. Like direct us in the like direction of features that are useful for that to that regard, and then it could decide like automatically or something, oh, of these 16 features we just found, these 10 are pretty useless, these 6 might have relevancy for alignment, let's just make experts for those 6 or something.
Yeah. It was basically that this naming convention seems very like brute forcey.
It's literally just the neuron number is all they're grabbing from. It's literally just like 34 million size model with the neuron number, this one, right? Yeah.
Whereas like, if you think about how you would like normally navigate like a library or something, we have that Dewey Decimal System where it's like, all right, this book belongs to this group of books and then this subgenre and whatever until we sort of get to where we want to go. And really what would be preferable besides like, is like, remember I was talking about over here with the, did I delete it or whatever? But remember we were talking about doing a binary search in a dictionary? Really what would be preferable is if instead of it being like in some like lexicographical order, it was in like a human thinkable order where it's like, oh man, I'm interested in stuff related to this. Now let's get more specific. Now let's get more specific until we get to wherever we want to be, right? I want to look at base 64 encodings. Now I only want to look at features. Now I only want to look at base 64 features that correspond to URL compression and so on until we get to our very specific feature, right? So the hope I would have here, besides like maybe having a more efficient way to learn these sparse autoencoders, is that you would have a because we're learning a tree, that the intermediate nodes would actually correspond to something meaningful or useful as well. You get what I'm saying?
Yeah, totally.
Yeah. I feel like that's not, I don't know, I feel like that's not obvious off first like glance that might be true.
Yeah, I mean, it depends on like the actual setup we're going, because we've like proposed a couple different possibilities to extend so far, like the raw duplicating of the hidden dimension and like no freezing or anything probably wouldn't do that super easily because you never know where the vector's going to go. Whereas like the MOE idea is more so like to that is like if it's actually being activated hierarchically in that sense, that's full on gives you the actual structure that you're looking for right there for the actual naming conventions. So that's cool. All right, interesting. This is exciting. This is a pretty good talk so far. I'm hyped. I'm just curious because you're talking about the MOE thing. That was what originally got me to like freak out and like ask you for the call, was when I saw you saying in the Discord like, oh, tree MOE of SAEs, right?
Yeah.
It just wondering implementation wise how you would do that. Like, is it literally as simple as using the, because I'm not fully understanding still like the base MOE that had the gating issues and everything and the more complicatedness. I'm still going off the simple model of just like an MLP with a hidden dimension on the inside.
That's why I showed you this picture, right? Even though there's all this gating mechanisms and stuff, you can still think of it as a single MLP with just a strange activation function, which is that jump ReLU.
Yeah, exactly.
Think of it as just a MLP with that jump ReLU, and it learns like a unique bias for each row.
And the up projection of an MLP is the same. It's just a linear layer. It's the same as a router for an MOE, right? Like, I wonder if it literally is as simple as using the actual activation from your encode, like from the encoder, the actual hidden dimension of your first trained SAE, and literally using that as like an MOE. I wonder if it's that simple, because like.
So I was thinking about that as well, and there's one like caveat or whatever. So there was a paper I looked at this weekend as well. It was called Switch Sparse Auto Encoders. So they took a switch router, which just chooses like the largest amplitude, and then they trained a bunch of SAEs based on like, so basically they just had a bunch of SAEs be experts for this reconstruction task, and then they trained a switch router to choose one.
Literally MOE SAE, yeah. Okay.
Yes. This is nowhere near as like expressive as what we were talking about.
Yeah, no.
Right? These would learn co-adapted features. And there's no like hierarchical or composition based representation here. Right. But what it did make me realize was that one, for what we're talking about, it would probably make more sense to use like top K versus a switch router.
A top K router, yes.
Yeah. Yes. But the other thing is that the router doesn't actually preserve the initial vector, right? So coming back to this picture right here, if we learned that this direction right here was an important one, and now we want to use our expert to sort of look at these differences, we need to make sure that we actually still add this vector in.
Yeah, you can't you can't literally just like in traditional whatever, you can't actually just multiply the expert by that number, by the router's number.
Yeah. So it can't just be oh, we trained a sparse autoencoder, now we have a router, and then all the children are going to unless the children have directions that look like the initial.
What's your YouTube channel name, by the way?
The J Den.
Oh, I think I know you. Yeah, Den. Yeah. Is that right? Bet.
Yeah. So that's one solution, right? Is like if we were to use the sparse autoencoder as a top K router, then we could initialize the children as just sort of looking like the initial vector, but with some noise for a group.
We can initialize the children. So top K router, let's assume we're also, just for simplicity's sake, also using a top K SAE, which is just OpenAI's version, which they literally use top K as opposed to ReLU or something like that. I wasn't fully clear on it, but it was a very simple edit, they said. And that way, because we're already doing a top K router, right, let's just use their thing. It also had fewer dead neurons. And then, so top K, and then you're saying initialize children with some noise. These little children expert SAEs, they also have to get as inputs just the raw X vector, right? Like they also have to just receive that as inputs. It's just we're deciding to go to them based off of the top K of our first SAE, right?
Well, this is what I was talking about. So by the way, I'm spitballing here. I haven't thought about this really as much as the other stuff, but that's part of the point of the call, right?
Yeah, for sure.
The point is if we treat our activations, so let's pretend this is our activations from our SAE, right? We have our X. It told us this is how much each direction should be used to
reconstruct
X or whatever, right? And these aren't the same as the actual vectors, right? So if I labeled these 1, 2, 3, and 4, then we might have a dictionary of directions, which is sort of our basis, right? And this, so direction 1 might be this, and direction 2 might be this, and direction 3 might be this or whatever, and direction 4 might be this, right? So maybe this is our dictionary. 1, 2, 3, 4. All right. This is telling us we should use this much of this vector, this much of this one, this much of this one, this much of this one, right? If we were to just use this as a router, we would lose this contribution, right? So there are two ways.
Because you don't want to initialize the expert just randomly based off the input or anything. You have to actually give this information to the expert somehow. I see. To grab that specific one. Okay.
So one way that seems possible is like we'd say, all right, these are the two experts that are going to get activated, right? We're going to pass this off to some other child SAE. So this is the tree of SAEs, I guess, that we were theoretically analyzing in the in the server, right? One thing we could do is we could initialize them with directions that basically look like their parents' direction, but just like diverged a bit, Like
initialize the weights of these expert SAEs with the weights of that part of like so one, right? The one arrow is the actual vector of the encoder matrix, right? It's the specific vector that got you that activation. You're initializing all of the weights of this new child SAE with the weights of that initial vector from the first SAE, and then plus some noise. Is that
Exactly.
right?
Yeah. So this is the original direction plus some noise. These are what these directions look like, and for this one, it would be more like that or whatever, right? I don't like this too much. There's a few reasons I don't like it. It seems like it would encourage dead neurons.
Yeah.
It also just like what I would prefer is something more like this. It's more like we just initialize it randomly, but or orthogonal to the original one,
Mm-hmm.
so that way it can learn the differences, which would make it more of a residual net. So that's what the thing I didn't think about before, right? If we need to use this, what we could do is we could just say, all right, this is what your parent said needs to be contributed to reconstruct it. So let's take the difference of what it says it needs and then learn the rest of it and train the expert on that.
So X minus the upward facing number one arrow.
Yes.
Okay. And so so you're effectively you're taking that whole feature out and saying, okay, but the difference between that feature and all of its nearby cluster features are still in there. So the upward arrow, right, is a feature that is hopefully in a cluster,
Yep.
hopefully. And when you subtract X, you subtract the up arrow like from X, you now have all the info that was still in X. You do not have the feature that was the up arrow, but you do have the info that was the difference, like the difference between the up arrow and all of its nearby in the
Yes.
same cluster features. You still have that information in there, right?
Yes.
And so what if you did both? I think you already said this. I'm just like re-saying what you said, I guess. So you do both of these things. You do that, you do subtraction, and you initialize your expert with the up arrow as its weights and some noise, right? Because now
I think initializing it as the up arrow wouldn't make a lot of sense.
because the up arrow's fully gone, I guess. The up arrow's fully gone.
I think what would make more sense is to initialize it with like a hypersphere that's one dimension less than this one.
Initialize the wait, what? Initialize the
So
weights?
so like it makes more sense in 3D. I think it would make more sense to initialize the expert with a circle on this plane.
Yeah.
A circle on this plane. So this is the original feature.
Uh-huh.
The child SAE gets initialized with a dictionary of directions, which is like a random sample of a bunch of points that are on a unit circle that's coincident with this tangent plane.
Yeah. Okay. And then they learn from there. So then when you actually want to get, so then if you had like a little circle of arrows out branching out from C, then if you wanted the original model's other vectors in, if the original model's cluster, you'd have to add those little
tip to tail. Yeah.
Tip to tail, right? And then plus a cosine normalization to get you back into the sphere again. And that would give you the direction of this sub feature.
Yes.
Methodology wise, how do you build an SAE on this one dimension fewer piece? Do you cosine normalize and then reduce the dimension by one? Is there a method to actually do that? Because when you cosine normalize, right, you are effectively only using one. You are using, whenever you have a vector that is cosine normalized, you are using one fewer degree of freedom than the vector actually has, because you are not using magnitude whenever you have a cosine normalized vector. Can you project a cosine normalized vector of length d onto a vector of length d minus 1? And if you can do that, I think then you can now just do an SAE on that d minus 1 space, right? Is that making any sense?
Yes. Like you're basically asking, how do we like know what hyperparameters to initialize the child with?
Yeah, how do we even get this slightly smaller, like literally one dimension fewer vector, right? Like how do we
So
establish
one
that?
thing is like constructing that doesn't require any deep learning. That's just like a math thing, right? Like we can use
Exactly. Yeah.
we
Yeah.
can use
I just don't know what math
cross
exactly to
product
use.
or whatever.
Okay.
I think
Yeah. Because you just
something
keep
like
on that
that.
same plane. Yeah.
That's a Google search.
Yeah. Exactly. Yeah.
That's I'm not too worried about that part. What I'm more worried about is like, it seems obvious that this neighborhood that's going to be in is probably going to be a lot smaller than 1. And so it seems like there's like a scaling factor that you would want to learn, right? Like
Okay.
there's a epsilon here essentially that it'll need to learn, right?
Yeah. To convert the space, basically, to convert this like 0.01 size magnitude hypersphere to an actual.
Yeah. Because
Yeah.
if we force it to do it in the activations, we'll start running into like floating point error. Right. Like if I do this 3 levels down, now my
it gets
epsilon
smaller,
is like
smaller.
0.00001, whatever.
And we need a fixed dimension. We need a fixed magnitude anyways for our weights of our smaller SAE, because SAEs are fixed. Yeah, whatever. Yeah, okay.
So we need to learn some scaling factor, but also, so let's write this down on the whiteboard.
So like multiply by said scaling factor, and then they can get their magnitude normalized, whatever is part of the usual thing.
What is that?
Interesting.
Self glitching. All right.
So that like what is even the loss function and everything then? Like how do you do it like a separate reconstruction? How do you add it back in for a new reconstruction? Like what's going on with that?
That's the thing too, right? We need to figure out how to estimate like group size. So something that I haven't thought about a lot because I haven't used it yet during this weekend was they talked about in these papers, they talked about a resampling technique. So there's a tendency in these autoencoders for neurons to die. Basically, they train a bunch of steps, right? We're talking about hundreds of thousands of steps, right? And they found that sometimes neurons would just die. Maybe the gate bias would get too big, right? And it would never fire for like 12,000 activations. And at that point, it's like, well, you're useless, right? So they would do this resampling technique, which is, I haven't implemented it, so I'm not as familiar with it. But essentially, they take this dead neuron and they reinitialize it with a different direction and hope that that sort of allows it to convert into something useful, you know? I'm not sure if maybe something like that would be necessary here, where it's like, maybe you would do that before the entire tree. Essentially, you say, was this tree useless? And if it is useless, then maybe I'll just clip you out and either omit you or replace you with something better, right? So I feel like this is, I shouldn't call this group, I should call this cluster. This part is a big like question mark to me right now. Besides hoping that it's correlated with these heights, right?
Yeah.
And this is also a bit of a question mark. Otherwise, it's like it seems more obvious what I would want to do here in terms of like spawning children and residuals and stuff.
My other question is just efficiency wise, like especially if you're starting off with very small SAEs, right? And then like do the expansion thing, like how do you ensure full GPU utilization when you have a bunch of these tiny separate SAEs? I guess like I'll be like, I guess to a certain degree you can just like use one single matmul for the up projection of all of them in a given layer, so and then just like split them apart after that kind of thing, like that's actually probably fine. But I'm just curious, when you get to like, this becomes very sequential, right? Like it's one thing to do MOE where you have one router and then go to experts and then you're done. But like you like multiple layers of routers, especially if they're relatively small compared to your actual GPU can handle. Now you're getting like serious sequential dependency when you go like 2, 3, 4, 5 layers deep on this thing, to where it's like, okay, we are for a given, like trying to run the level 4, like 4 depth down experts. Now suddenly it's like,
Yeah.
well, we only saturate the GPU when we actually hit that 4th level. When we're at that 1st level, we are using 0.01% of our GPU type thing for that actual kernel call. This is a nightmare. Like, how can you, instead of making it fully sequentially dependent, I don't want it to be that way. How could you instead make it such that you're actually running the topmost SAE node in parallel with the bottom ones? Like, we're just like, that's what I would want to see. Because if you can't do that, suddenly you have massive GPU downtime.
Yes. So, okay, there's a few things, right? One is that if we do use the residuals, like we were talking about before, the operations become independent, right? This is sort of like a functional programming thing, right? But like, if I don't need the results from the previous layers, then I can do it in parallel. But I guess one thing I'm thinking about, right, is like for these top K, I sort of wonder if you could just learn a mask, right? Versus like computing each one independently and then sort of aggregating them after the fact, where it's like you would, if these are sufficiently low, you would have them go like -6 infinity and do like exp on them or something. You get what I mean? Like,
yeah, we're top king or whatever. Learning a mask, and I'm not quite, I think I almost imagine, I'm not quite sure I understood what you said. I'm almost imagining, when you do this, taking not only your top layer, but also your second layer and your third layer, doing them all actually in parallel, effectively like sharing their encoder, the exact same matmul and the exact same like on encoder and decoder, right? And then effectively saying, okay, once you have the output from all of them, then we can go to the topmost layer and use it to make our mask for the second layer, and in parallel use the second layer to make our mask for the third layer, kind of thing. And I don't know if I'm making any sense now.
well, yes.
I wasn't talking about your talking about. I lost track. I was off on a side tangent, but yeah.
No, I think what you're saying makes sense, right? Like, it seems true that we kind of already do this with the gate, right? With the gate, we compute a bunch of contributions, activations, right? And then we also compute a bunch of we compute a binary vector, which tells us whether we actually include the activation or not.
Yeah.
But so for each vector, there's going to be a bunch of wasted activations essentially that don't get used, right?
Yeah.
It seems like that would also be possible with the tree, right? Where it's like I could calculate what each of these residuals should be, and then only choose to use the ones that are actually like selected, right?
By use a mask, we're on the same field. We're on the same. I think we're on the same thought train here. We just like we're using different words. I think you're totally. I think we're on the same thing right now. Yes, like compute them all densely, then use a mask or move them after the fact, the way you do with like a yeah.
The only problem I see with that really is that that's just not like how MOE works.
Yeah, no, just right? Parallel GPUs and everything. Yeah, no. Yeah.
I don't know. It's gonna take some thinking. One thing I'm trying to think about too is the loss function you were talking about. What does the loss function look like?
Yeah, like is it adding back into the original parent model's reconstruction error, or is it doing its own reconstruction error? I would assume add back into the parent model, because you wouldn't want to just pick up on random other features or anything. You wouldn't want like duplicate stuff in there. Like, I'm not quite sure. But yeah, I don't know how you would set that up.
I think it would still make sense to have that. I shouldn't call it triplet loss. Triplet loss is a separate thing, right? But I still think it would make sense to have those three components in the loss, which is essentially what is the final reconstruction that this model is creating, and how faithful is it to the original activation vector. So there would be a change here, I guess, right? Well, here, let me say what stays the same first. We also will want to have a L1 penalty on the routers so that they're sparse, right?
And the router itself is maybe just the encoder, the parent model, so that's already there.
Yes.
Yeah. Okay. I'm keeping with you. All right.
The thing that might need to be slightly different, but I still think would make sense, is we still want the auxiliary loss, right? We want to see how faithful are these activations before they get gated, before they get sparsified, right? And in the case of this tree, it might make more sense to ask about how faithful the reconstruction is to a residual rather than the original X.
You keep saying residual. I'm not sure I'm following.
So like right here, right? Let's say X was this vector.
Oh, that residual, the difference between. Okay, I got you.
Right
yeah,
here, this middle one. Yeah.
Oh, so the sub experts, whatever, they contribute and they have a reconstruction thing, both for their contribution to the main reconstruction loss, and they're also doing a separate thing for their little residual piece.
Yeah. And their contribution to the main one, I don't think would be component wise. I mean, obviously it get updated in the back propagation properly, but like it would literally just be when I evaluate this model as a whole, right? Like what does it evaluate to compared to the original X, right? Yeah. But I'm saying, for how do we actually keep these, how do we make sure that these routers have useful behavior? We look at the difference between what the parent node suggested and X, and we tell it to learn that. And so then we would say, when we look at its reconstruction, we want to look at the difference between what it outputs and this versus what outputs and that. Because then it actually has a niche that it's learning, I guess, right? It only has to learn a difference versus having to learn an entire like representation, right? Because this would also allow that's the main benefit of a ResNet in the first place, right? You allow it.
Oh, you're also saying residual, and that's, I thought you meant like error residual term, as in like the subtraction of the thing. But you also mean like ResNet, like you're going to add it back onto the previous one's attempt.
Yes. But that's that's the same residual, right?
Yeah. Okay. Yeah.
You might not
theory,
because
you're doing the add thing. Yeah. You're a more theory guy than I am, it seems. But yes, I see your point there. That's just structure wise. I'm thinking about like, okay, using residual makes sense there. That's cool. So you want to so there was the initial big model that has reconstructed X tilde, right? X whatever hat thing, right?
Yeah.
You literally want a residual on top of that with each tiny MOE version and test their component-wise reconstruction, right? Like ResNet style, as well as just the main models. Interesting.
So because that was what I was talking about here, right? Remember I was saying that I don't like this. It's not just that I think it would encourage dead neurons, right? But I'm forcing this child MOE to learn a faithful representation of the original vector, which is like a lot, right? Like the original ResNet, that I think the example is upscaling images, right? Mm-hmm. The whole reason it's useful is because you can allow each of these blocks to only have to learn the difference between the bad quality image and the high quality image, versus if you didn't include these residuals, not only would it have to learn how to upscale it, but it would also have to learn how to actually represent the original image itself, right? So it's like if I have a low quality picture of a bird and I want to make it a high quality picture of a bird and I don't use residuals, I have to learn how to encode a bird in my latent space.
Yeah, which is a whole diffusion thing at that point. Like that's a whole separate.
If I use the residuals, I don't have to actually learn the representation of the bird. I only have to learn the difference between a high quality bird and a low quality bird. I feel like something similar could be said here, right? Where it's like if this is cat and then these are all like, species of cats, it makes more sense to just learn the difference between the general cat vector and the species ones versus having to also remember this is how you represent a cat and then here's how you represent a cat and its species. That's just a lot more information to encode, right?
Yeah.
So that's part of why I'm thinking about that little projection onto the hyper tangent, whatever you want to call it, right?
And so when you're doing this, like the smaller the child one has to now reconstruct on top of the. So is the input to a child expert, a child SAE, is the input to its x tilde x, because you're doing residual, right? Does it get as input not x raw but x tilde? Or no, wait, no, because that's a yeah. I'm confusing myself at this point.
The final reconstruction.
Yeah, I'm just like, what is the actual residual? Like, what are you connecting to? Like, how, like, what's getting added, right? So, like,
so if I were to label each of these,
my brain's getting tired.
E1, E2, E3, E4, then I might say, let's call this W1.
Oh, you're doing a residual on the actual weight vector. Wait. My brain's getting tired at this point, is what I'm noticing.
Yeah, we might need to take a break or resume this another time. But let's say these are our activations, and then these are labeled E1. What is going on? E1, E2, E3, E4. Those are so slow. There you go. Then let's say we want to train an expert on this activation because it was high. It would receive X minus A1 E1.
Okay. That would be its input. Yeah, that was the whole subtract thing earlier. It would receive that. And then with that as input, it is its own SAE expert, right? It's its own SAE. And what are the weights of its encoder? Was that still a weird thing we were doing? Were we still doing that, or were we not? Or
that's what I was talking about, where it's like, how do we initialize it? I don't think it makes sense to initialize it with its parents' weights, because we run into this problem I was talking about, where it's like, oh man, like why does it have to understand how to encode E1? That's the whole point of it being E1's child, is that it can forget about E1.
But
right?
It also doesn't make any sense to have it just reconstruct this X minus A1 E1, because now it's, if anything, discouraged from finding anything in the same cluster as E1. Like if you subtract out E1 and you say reconstruct this thing that doesn't even have E1, then all of the actual magnitude, the importance of all of your tangent plane arrows around E1 are pretty small in comparison to all the other shit that is in X, right? And so if anything, when you take as input X minus A1 E1 and you say reconstruct this, you're actually telling it reconstruct everything except E1's cluster.
I get what you're saying. Yeah, you're right. I almost wonder if it would make more sense to
like add A1 E1 or something. Like the opposite almost.
This is a projection thing. We need to think about projections or something. You're right. It might make sense to only worry about, like, we want to remove the other stuff.
Oh. Well, okay. So that's useful in making sure it doesn't try and reconstruct A2, A3, and A4, but there is still a bunch of shit in X, other clusters that were never picked up in our first four, our first four features. So there's still a bunch of shit in X that we have to worry about. That's probably more important.
The original hypotheses, right? We have our superposition hypothesis and our linear representation hypothesis. The whole point of thinking about an SAE and thinking SAE might work well is that we can faithfully reconstruct the activation from only a few of the directions. So we don't need to think about all of these and their little minor things, right? The assumption is that there is a cutoff here that we can make, like It'll be different for different heights, but let's just pretend it's the same. Where if we only include these two, it will make a faithful reconstruction.
Mm-hmm.
So like we don't need to worry about these per se. I get what you're saying now about the loss not making sense on the residual. It does still seem like you could.
There's something there for sure, but
it can learn because this is happening for each of the ones that do get activated, right? It's not like it's only happening for this one alone, right? It would also happen for the other K direction arrows in the dictionary, and each one. So that this is where I don't know if it's introducing some sort of weird dependency where it'd be like, oh man, let's project all the differences from the other children away so that we only have the one that's relevant to this expert, or if it would just learn that.
But my thing is like I get the whole like importance whatever, but and you said there's like the threshold, and I know it's per which one, but the difference between A1 and all of the vectors inside the same cluster as A1, the actual like different hyperplane or tangent plane things, is still probably a lot smaller than the not even yet seen A5. Like the original, this thing right here doesn't even have an A5, right? We don't give enough neurons to do that. The length of the tangent plane vectors off of A1 and their importance is probably smaller than A5. And I think that your child SAE will just grab A5 instead of worrying about the little tangent vectors off of A1.
Yes. I was this is part of what I was talking about with the scaling factor thing too. Where it's like these are obviously much smaller, right?
Yeah.
But if we're thinking about like how it's represented in a sparse autoencoder, usually we have these directions as unit vectors. I still think it makes sense for them to be unit vectors. It's just that you would need to learn how to scale it down properly. Right.
Like what exactly, I get the conceptually what we're trying to scale here, but like math wise, what do you scale to get those up? Like what can I even, let's say we have our correct scaling factor. What is the input to the scaling mechanism? What are you actually giving me that represents these tiny little vectors on the tiny tangent plane vectors? You know what I'm saying? Like,
I think it would be new activations with the new directions, but there'd have to be a third thing, which is like the how much to scale it down because it's a child. I don't know what you would name those or whatever. Maybe they'd be epsilon 1, epsilon 2, or whatever, and so on.
I'm not clear here. I'm not sure I understood that. What are you going to put into the input? Like, what is the actual vector I'm getting?
Like
is the problem.
What will it use to determine what they actually are? Is that that's what you're asking?
Yeah, like before you can even like scale those little things up, how do you even get those little things? Like, what is the actual input to this scaling mechanism that then lets us do the whole thing? The way I see it is like what we currently have, which is either x minus a1 e1, which was you said was not the one we're going to do, or even just x minus a2 a3 a4 whatever. Like when you scale that up, you're also scaling up a5. Is my problem. Like I don't see. So A5 is a theoretical. We never actually made it because our primary, our parents SAE only had 4 neurons, only had 4 actual hidden dimension. A5 is just the 5th one that could have gotten picked up if we had 5 neurons, right? I bet A5 is still bigger and of more importance and still in X than all of the distances of A1 to all of its little tangent hyperplane pieces. Like I don't see how we're picking up. I still don't see where we're getting the thing that we're going.
So you're saying
hyperplane stuff.
There's a problem where not all of the original vectors necessarily belong to a cluster, and there might even just be a whole new cluster to discover.
Yeah, I think it'll just find different clusters as of the input I've been told now, which is x minus a2 minus a3 minus a4, like, or I guess it's a2 e2 whatever, but like whatever. Like,
okay, so this is something I initially thought of too, right? Calling this a tree is a little strange.
Yeah.
I think it's a good mental tool, but usually when we think of trees, we think of the children being completely like independent, right? And that's like part of the utility of the interpretability here. And I think it is possible that even if you had like a hierarchically organized like tree-like structure here, that doesn't necessarily mean that they're actually independent in the like linear algebra sense, right? Like for example, you can imagine if all of these vectors belong to some, you know, set, we might be able to partition them into pretty reasonable like clusters or whatever. It's like, all right, these are machines and these are animals and these are like grammar words. These are programming terms and stuff. But there's going to be some overlap just in terms of them sharing some dimension. And you might like sometimes we do weird stuff. This is the sort of stuff that LLMs like have trouble with sometimes, where it's like we combine stuff because we're whimsical, right? Where
use
it's like
idioms and whatever, and
yeah, like, well, you know, I have a melancholy purple whatever, right? Like and that has some kind of tractable meaning. And so something to keep in mind, I think, is that there will be some collinearity among the children here. I think it's sort of inevitable, right? Like these can't be completely independent. They could be almost independent, especially as we get into high dimensions, right? We have a lot of near orthogonal vectors. But I don't think it would be completely independent in the same way that like a decision tree is, or something, right?
Yeah, so that's a good point, and I'm not sure how it applies to what I was saying exactly, but it's a good point, and it makes me then ask the question, okay, whereas with with like a simple just one layer, not all of our bullshit SAE, right? What you've got is you're removing that collinearity by encouraging the sparsity and encouraging individual features, right? You're partially removing it, it's trying to kind of thing. And then when we do our children and we have multiple different children SAEs that are all running parallel separate, right? How do we prevent of our like different children SAEs we make, how do we prevent all four of them from picking up on the exact same or nearly same like highly collinear features? Like, would it just be like, how do you prevent?
So that's something that I'm not sure that we have to worry about it too much, right? Like let's think about what we were describing before. Let's do a little experiment, right? Let's say this is where my children features live for this one. And this is where my child features live for this one. Can they even be collinear?
Okay, so if we have that as input, if we can get those, then yes, I'm happy with that. I'm totally on board again. But like, this is back to my early question, is I still don't understand how we can even get those planes, those tangent planes.
These?
Yeah.
I feel like that's just a mathematical trick, right? It's like
I'd like to see the trick. Does that make sense?
Okay,
Like,
let's do it for a low dimension, right? Let's do it for a complex number, right? Complex number. What does the unit sphere look like? It looks like e to the I theta, right? Okay, so I have e to the I theta. What is going on, dude?
This might just be my brain being dead by this point, because I'm pretty sure it is. But like,
it's a good exercise, because it's not clear to I'm sort of making an assumption here, but it's not clear to me either that it's actually probable for them to be orthogonal as well. It's sort of hard because like this picture is bad because we're in 2D, right? Like I wish we could visualize stuff in like 300 dimensions or whatever, right? But like we're supposed to imagine that these vectors are all orthogonal
Yeah, yeah,
somehow, right? And so I'm sort of assuming that these would also be orthogonal, even though in the picture they're not, because there's just more
yeah,
room for there to
yeah.
be them
I,
to be orthogonal,
I'm cool
right?
with taking them as orthogonal. It's just still not clear to me
How you
how
have
those,
I
like,
have this is one of my directions. This is one of my basis directions.
mhm.
We can represent it as e to the I theta, right? This is e to the I. I'm gonna just call it
T is
t.
good. Yeah.
Yeah, right. If I
And
want
then,
this, then I need all of the vectors that are orthogonal to it. In 2D, that's just going to be
the
I minus
whatever
I.
product. Yeah, yeah.
So basically, I have a line that it could live on. I have a line which is this line right here. And how could I parameterize this line? I could say this line has a direction and a offset.
Yeah, and it's okay. I think I'm got what you're going here. Yeah.
So I would say like, okay,
So you think that this is a pretty like a that we can derive it right now? I think I agree with you. This is a pretty simple like derivation to get just an orthogonal plane to the that's on the point that at the end of the thing. Okay. All right. I think I'm probably back
it
on
would be like
board.
IE to the IT x minus e to the IT, where x is a real number. Right.
Yeah.
So IE to the IT would be this is like back to like those like remember way back in like high school when they taught you like here's how you represent a line with vectors.
Yeah. Yeah.
It's like all right,
Yeah.
my
And
orthogonal one, that's this. And then I can
I think I'm
scale
with
this
you here that this is just
to
a
any
simple
real
transformation, and
value,
I was freaking out about it. Yeah. I
right?
think I've got you.
And then I need to make sure that I
Just shift it. Yeah.
shift it. So maybe it would actually be a
Yeah.
plus,
This is
right?
literally just like put like for taking so what we so this wouldn't what we would do for the input to the child's um expert SAEs, right? Is we wouldn't do X minus A1E1 or the whole A2, A3, A4 one. We have a relatively simple transformation that just looks like putting things into, in this case, polar coordinates. And then to make everything orthogonal, you can just do something like subtract by pi minus 2 in that dimension, or like the equivalent for using pi minus 2 as the actual degrees, I guess. And
Yep.
then
And
do
only
a shift offset of the actual original vector. And now suddenly you have that hyperplane.
and that shift offset is already taken care of by the residual. So we really only need the hyperplane.
Yeah. Yeah. And the
So,
hyperplane is, do you think that's it? Is that the correct one? Is that the hyperplane itself? Like the
well, I probably wouldn't use complex numbers for it, but I'm
yeah.
sure there's some formula I could look up
All
that's
right.
just like, here's how you represent the hyperplane in terms of like the original
Yeah,
tangent
the
vector,
perpendicular hyperplane. Yeah, okay, I'm back on board. I thought this was, I would like to see it still. I'd like to find out what it is and just like to see it and to
yeah,
confirm
I
that
don't
it's
remember how to do this right
computationally efficient
now.
and everything, but I was getting very caught up in like how do we actually find that? No, I think you're right.
Yeah,
It's finding
I think
just
it's just a given.
literally the perpendicular hyperplane, then shifting it by our actual dimension, and then just initializing a bunch of random vectors on the hyperplane. All right, I'm back up to speed. I do
And
think though that yeah. Go ahead.
the only other thing that we have to worry about is that we want to make sure that when we initialize it, that they have unit norm. So we still need to have the constraint that this has a norm of 1.
Yeah, yeah. And then I do think
Well,
that was proof though that my brain is fucking dead at this point. Like I'm done. But this has been a lot. This has been a lot of fun though. That was good. Like you just like I was like, oh shit, this is just trick again. All right, never mind. Bet, but that was good. I gotta call it there though.
yeah, yeah, yeah. I give some time to think about how to actually. I need to convince myself. So you've shown me I need to convince myself that the child vectors are actually orthogonal, so that they don't co-adapt.
Yeah, with an A5 or
And
whatever. Yeah.
um, also that I need to think about like um, a, a, a loss function and a representation in memory that's going to actually be efficient on a GPU. But
Yeah,
I
that's always a big thing. Yeah,
in and of itself
and just
is not a
how do we
bad.
order all of them and everything. It doesn't matter too much for your word to vec whatever, obviously, but for it to be worthy of even just sharing, if at the end of the day, if we're stuck with some crazy sequential nightmare, then it's not going to matter, kind of thing. Like you need to, like, what is the actual of the sequential version where you actually have to do parent node and then first layer children, then second layer children? What is the actual utilization of GPU at that point? Well, it's if we're multiplying by 2 each time for children, so like an exponential increase at that point, then the amount of GPU you're not using up is like over half. It's that whatever exponential log, whatever the fuck, right? Like, so you need to figure out like a way to do this in parallel for sure, like parent nodes and children nodes all at once, basically.
What I sort of wonder is like to solve that problem you were talking about, where it's like, oh man, well, what if since we gave it a bunch more room, now there's whole new clusters for it to pay attention to that weren't even there in the first place, right?
Mm-hmm.
One thing is like, I do think that families of clusters could belong to the same parent node. That's what makes it a tree and not just like a single level list, right? Like you could have a parent node and it ends up splitting into 3 families that are separated, right?
Mm-hmm.
But we know from these papers that a lot of these nodes end up dying and we have to resample. And so that resampling opportunity might be a way to get the new space to be utilized for new clusters without having to like destroy an existing hierarchy. Right? Like if I've already identified this direction corresponds to this cluster and I want to split it, this other direction is useless. It's dead every time. I'm going to just allow it to explore a new direction and it might discover a new cluster. And then that's just a new one.
But we can only do that, at least in terms of a totally new cluster, like a totally new one, at the parent node SAE, right?
Not necessarily. I mean, there might be dead nodes in the children too.
Yeah, no, and I'm cool with like in their sub context, like there's clusters and clusters, obviously, right? Like if you actually look at one cluster, you can probably see some denser and lighter regions in that cluster itself. I'm cool with like, yeah, we can do the reinitialization thing in there, but like, what was it? What was I?
But you're saying for a wholly new cluster, it would
For
probably
a
be at the first level.
straight up original new cluster, it can only happen in the most parent node, right? Like there's like thinking about it in that sense of like making sure that, which I don't think is an issue because we just established the whole like perpendicular hyperplane tangent thing, right? So I think we're probably fine on that if we can figure that part out. My brain's too dead at this point though. I think I'm gonna keep asking dumb questions. Let's call it right here. Are you hype enough about this to just like you're gonna be working it for a while? Do you think? Or you like? Because I think you should. I think it's really cool.
I was just say I feel like this is like a cool idea I've had, and I feel excited enough about it that I've been working on it, and so maybe I should just continue and see if I make notable progress. Yeah.
I think you should continue. And I think it's like if you can just figure it out and get it working, I think it's like what it promises is pretty fucking huge in terms of like that's worthy of being the talk of the week kind of thing. In the field at large, like if you can make SAEs do this, how the fuck whatever like this ends up being, I think that's worth like a paper of the week on all the websites type thing. I think it's that cool, even if it's just on a GPT-2 small 100 million parameter type thing, just for demonstration. It works obviously word dev because who fucking cares? But like everyone wants to see a fucking LLM because they want to see a fucking LLM because they're you know what I'm talking about. So still doing on that.
The only reason I didn't do it for LLM is just because I've never worked with the PAL data set, and also just looking at features and understanding them is going to be slower. Right?
Yeah. No, I wouldn't actually test and try things in an LLM. I would do everything on your current setup with your word vec, and then like at the last moment we're like, We're
Yes.
writing the paper now.
Thinking.
Like
Yeah.
it's like, oh, Evan's gonna go write some intro documents, and Jaden's gonna go rewrite the code to fit on a GPT-2 small, like just like refactor everything basically. That's what's actually
Yes.
gonna happen, kind of
Yeah.
thing. I think you're totally good there. I've got like, I don't know if you want more help just in terms of these talks kind of thing to shoot shit out. I straight up would like heavily consider like helping kind of thing. Like starting next month or so, something like that, because this is cool shit.
Cool.
I like it a lot.
Yeah.
That so keep me updated, man.
All right, yeah. And let me get that recording so we can have a record of this too.
All right, bet. I think, did you ever hit the record button? Or is it
Bruh.
just live stream? I think you're gonna have to like download it from my channel as my guess, because I don't know how this actually works. And I know that the live streams get saved, so we might be kind of fucked.
It's fine.
It says live and it's recording. It does not say start recording. It says start recording. So I don't think there is one. Although there's recording, is like the live stream has a recording, obviously. I think it'd be fun to chop this up kind of thing and do it that way. But yeah, I don't know. We weren't prepared enough to know how that works, I don't think. Everyone who's still watching, go watch Jaden's channel, the JDEN.
You start posting more. There's another project I've been wanting to work on that I've been working on for like a long time, but like I haven't been, I don't know, this got me excited. It actually started getting me like coding, and I made good progress in even just like a weekend. And so
it looks like a lot of fucking progress for a weekend. Yeah, no, honestly.
Yeah, like that
nice
code
job,
was like 2 days.
Yeah. I think this is fantastic. Like, awesome job. Legitimately, this is so dope. But
thanks, yeah. But so you let your brain recharge, and
appreciate it.
We could do updates if we make progress. Yeah.
Yeah. Whenever, yeah. Like, hopefully, I'm so down. Yeah. Next time I can hopefully keep up with you. But yeah, good talking to you, man. I'm gonna end it there.
If that would be useful.
What's up?
I could send you the papers that were relevant too, if that would be useful.
I think I saw them all except for, I don't know that I ever read the original SAE ones. If you can ping me that'd be nice. But
yeah, like the gated.
Yeah, the actual in-depth one.
Yeah.
All right, cool. Good talking to you, man. See you.
Let's call it. See you.